Recording progress.
Yeah, comes on everyone. Let's start off. Last thing that we are doing, we started with units and dimensions. Yeah, comes on everyone. It was an easy chapter compared to kinematics and stuff, but an important one. Great, let's go ahead. Next thing. Order of magnitude. Others do keep your cams on. Perfect. Let's go ahead. So what is this order of magnitude? Again, just a convention there. So, so if you have a number, right? So basically it is defined as the someone does not keep the cam on. Please keep your cams on. Yeah. So it's basically approximate size or measure of a value. So example, I think the best thing would be with the thing. So if you have something like A into 10 power B, so here B is the order of magnitude. So we have some rules here. This is the case when if A is less than equal to 5. If A is greater than 5, then the order of magnitude is B plus 1. Simple thing, but these kind of questions were asked in bits and CET. So let me show you some examples. So if you have something like 6 into 10 power 3, you can clearly see this number here, 6 is greater than 5. So we actually kind of round off this to 10 power 4. The order of magnitude is 4. Suppose if you have something like 3 into 10 power minus 2, this can be rounded, that is less than 5. So we write this thing as 10 power minus 2. So the order of magnitude is minus 2. Suppose if someone gives you a number like this, 4.57 into 10, 457. Then what you do, first you round it off. This is 4.57 into 10 square. You bring it to one decimal. And then you will say, okay, this number is less than 5. So this thing becomes 10 power 2. So the order of magnitude is 2. If you have exactly 5 into 10 power 1, then we still write this as 10 power 1. So less than or equal to, anything equal to less than 5. So we are following NCERT. In some books or something, they might give you something else, less, greater than or equal to 5 is B plus 1. But NCERT, this is there. So we will follow it blindly. whatever is in NCERT is the right thing. So here order of magnitude is 1. That's it. Nothing big, but you should just know. Maybe I'll just give one more example. Let's say someone gives you 0.012, something like this. You write this as 1.2 into 10 power minus 3. So you always have to bring it to one decimal. Clear with this? That is simply order of magnitude. Next thing. Any doubts on this? Any other number you want to try? So you need to get that first number there and then you just finish it off with that. Great. I think one or two are new. So first thing, again, like I said, there's no need to write the notes. You will get the PDF. So focus on listening, solving the questions. That's where you give the priority there. I give you a question, you got an answer, you can type in the chat box here. As just said here, you can type there. Anytime you have any doubt or something, please don't hesitate. You can always raise your hand or unmute and you can just ask me. The next thing, significant figures. Now listen to this. These are not difficult, but there are rules and everything. So, and especially when you do your, integer questions, you have to round off up to 2 decimals and all the rules are based on this. Significant figures. And we'll call this thing SF. So what are the significant figures? So these are the digits in a measurement which are reliable. The whole story is like this. Let's say you do an experiment somewhere in Australia, some guy does an experiment somewhere in London, and some guy does in Bangalore. The thing is, how are you sure, the instruments they're using are actually good? And when you see the same result, right, two people can give two different results. For example, let's say we have a scale. Let's say this is 6 and 7, and let's say the number comes somewhere here. Now, if someone asks this question, right, what is this exactly? Now, let's say even in this, there are, the smaller decimals, something like this. The problem here is we are sure it is 6.4 something. After that, I'm not sure, right? Some people will say, it looks like 6.44. Some people will say 6.45. So we are really not sure about this thing. So 6 and 4, everyone is sure. And maybe the last one, I'll say 4. Now, if you see the 6, the first digit is your most reliable digit. And that 4, the last one, is your least reliable digit. Meaning that last digit, we are really not sure. If I show this to someone else, they'll say 6.45. Someone else will say 6.44. So in this, what we say is that 2 significant figures and the last one included, we say this thing has 3 significant figures. So this thing, right, is not exactly physics concepts, but people started having problems with measurements. Everyone started measuring with whatever scales they want and whatever things they need. There is no one common thing. So people said, yeah, this won't work. Tomorrow, if you're going to publish a paper, you stick to the rules that we have. So the significant figures, right? So the one of the main rule is this: when you want to use SF, it is supposed to be used for measurements, with accurate instruments. SF is supposed to be used for measurements which are done with accurate instruments. So that's the first thing. But then we will see if you start using some, not reliable instruments are bad, they're really not that accurate. You start getting really weird answers. So what are the rules for this? So rules for significant figures. The first rule, all non-zero digits are significant. That is 1 to 9 are counted as significant. Second thing, zeros before the first non-zero digit Manav, adjust your cam. Anish, Aniket, adjust your cams. Make sure your faces are visible on the screen, everyone. So zeros before the first non-zero digit are not counted. And the best way to learn is with examples. So example, if someone comes and tells 0 to 3, that first zero is useless. So we write this thing as simply 23. This has 2 SS. If you say 0.631, that 0 is the first zero on zero digit. It's not counted. So you're supposed to write this thing as 6.31 into 10 power minus 1. So you should never write in your, tomorrow if you write a PhD thesis paper, right, you should never put a number 0.631. They'll expect always you'll write in this form 6.31 into 10 power minus 1. So this thing has 3 significant figures. Suppose if you have 0.00123, and this is simply 1.23 into 10 power minus 4. This thing again has 3 SF. So all those zeros before the first non-zero digit, you don't count them. These are not counted. But if you have something like this, 0, 0, 1, 0, 4, 0, 0, 1, these are the zeros before the first non-zero digit. These are not counted. Yeah, but these zeros are counted. So we write this thing as again like 1.04001 into 10 power. How much is that? 1, 2, 3, 4. 10 power 5. So this will have 6 SF. So zeros between non-zero digits are counted. Between non-zero digits. Any doubt so far? Because the zeros before, right, they really don't mean anything. They don't give any measurement. So the idea is this. You write in this form, then there'll be no confusion that initial zeros are useless. They really don't tell you much. Third one, zeros after the decimal are significant, assuming you follow rule number 2. For example, if you say 2.30, that zero is important. 3.002, this is 4 SF. If you simply say 40.000, then this is a 5 SF. But if you write 500, this is a good one. Now, if you write 500, right, these zeros are not counted. I'll tell you why. So this is supposed to be written as 5 into 10 square. So this thing actually is only 1 SF. So if you say, no, I want to count all the 3 digits, then you're supposed to write it as 5.00 into 10 square. Then this will have 3 SF. So let's talk about that. Why you write the 500 like that? Suppose if you have again 0.01, if you see, right, this 0 is not counted. If you're at 0.0100, this thing is 1.00 into 10 power minus 2. So this thing again has 3 SF. So basically these 3 are counted. So the second rule says if you have a 0 before a non-zero digit, that's not counted. Third rule says if there is a 0 after the decimal, you count it. So you have to follow the second one, and then the third rule applies. So last two zeros are counted because they're after the decimal and there is a non-zero digit. But if you have something like 2.0100, then all are counted. I know the rules are like that. So 1, 2, 3. There are 6 SF. The fourth one. Constants have infinite SF. So example, if they say number 3, so that means you're sure it is number 3. It's like I have 3 apples. You're pretty sure there are 3 apples. But if I say it's a measurement, the length is 3 centimeters. So that is how you know whether something is a measurement or a constant. You will see a unit there. So this thing has 1 SF. This is a measurement. So be careful with that. I was supposed to keep everywhere centimeter and everything. I didn't. So maybe I should write here centimeter, kg, and all that stuff. So, but that units are important. Now, what is the story behind 500? So first thing, right? People had a problem. If you have a scale, let's say the scale is showing something like 6 and this is 7. And let's say the reading comes somewhere here. How should I report this? Should I say this is 6? Should I say this is 7? Or should I make a guess and say this is looking like 6.4? So this is one problem people faced. And people said, no, we are not going to guess this, right? We are going to do what? When if you have a measurement like this, when you look at this, you get a feeling, oh, it is looking pretty close to 6. You will report this answer as 6. That's it. You won't say 6.5. You won't say anything else. You won't guess a number. If it is close to 6, then it is 6. If you feel it is close to this side, it is 7. Same way, for example, if you have something like this. And let's say your measurement comes somewhere like this. Now here there's a judgment call, like, it is 6.6, I'm sure, 6.7. I feel it is close to, that 6. So I will report this as 6.6. So you report it to the closest thing. So this is how everyone decided. When you see a scale, you don't guess that unless you have a measurement there. Now, because of this, what happened? Now, because of this rule, now if someone comes and tells me my length is 500 centimeter, you know the meaning of this? When you say 500, this is what I will start thinking, because from the rule that we have, that means you have a scale where that scale ka measurements are so bad, 400 centimeters, 500 centimeters, and 600 centimeters. There's nothing in the middle. There are no divisions. And your value, right? If it is below 550, if it is here, I will say 500. If it is above 450, I will say it is 500, isn't it? From that rule that we have, I will always take the nearest number. Now that means this 500 centimeter, this reading can be anywhere between 450 and 550 centimeters. It's a very bad measurement. Then you say, no, sir, I actually mean it as, 500 and, it is not this bad. Then maybe you should report it like this then. 5.1 into 10 square. Sorry, if I say 5.0. 5.0 into 10 square. Now, if you report like this, because of the decimal, what I will think? I will think, okay, your scale is like this. 500, 510, and 490. So that one decimal, right, will tells you what kind of instrument you are using. So those decimals are important. So without even asking the other person, boss, what kind of scale did you use? I can see the decimals and I can figure out what kind of instrument did you use. That means here the measurement lies between 505 to 405, 495. So this is between 505. It's an easy chapter. It's all rules and stuff. It's unlike kinematics, but People do go for and come. Now, if you say, no, I actually mean 500, then yeah, great. Then you should say 5.00 into 10 square centimeter. If you see, they all look the same. They're not same. When you say 5.00, I know, okay, this guy used a scale with two decimals. That means on your scale, see, I don't even know what kind of scale you used, but I can guess from here, 501 and 499. That's the meaning of it. So that means you are between 499.5 to 500.5. This is a pretty accurate measurement. I have three significant figures. That's the reason this thing has only one SF. Meaning I'm only sure about the first digit. The remaining are messed up. So this thing is supposed to be written as 5 into 10 square. This thing has one SF. This thing has two SF. This thing has three SF. Are you clear with that? Why the decimals are counted after that zeros? So if you say something like 5.000 into 10 square, means your measurement is, you must have used a really good scale. It's 409.95. 500.5. So your scale must have been so accurate. This thing has 4 SF. All clear with this? The difference between 500 and 5.0010 square. They look like 500, but they're not. That decimals are telling you what kind of scale you used. So tomorrow when you report, right, the length of the, the resistor which we used is 3.00, 0 centimeter or 10 power, whatever, minus 2 centimeter. It is understood that you are very clear up to 3 decimals. That way. Clear with this? Simple stuff. So let's see one question on this. I'll give you some questions. You have to just tell me how many SF are there. There. Just finish it off manually. You don't need to type. It's, this stuff. Find the number of SF. Shrikant, can you keep your camera on? Done? 3.2. 2 SF. 4. This is 1. You're supposed to write this as 4 into 10 power 4 centimeter. This is 1. If you say no, all are important, then you write it as 4.000 into 10 power 4. This thing, the starting zeros are useless. So this is 6. This thing is infinity. This is a number. If you see, there is no unit here. That's what, if you observe that I wrote everywhere units, I didn't write anything here. This thing is 2. This thing is 4. 4. The first zero is not counted. This is 5. This is 6. Clear with this? Do check it out. Anyone not clear with anything here? Ask me. Check your answers. What is 0.0? How many SF this thing has? Remember the second rule? All zeros before the non-zero digit are not counted. There is no non-zero digit here, 0. This is useless. 0.0 means nothing. It has 0 significant figures. Yeah. Next thing, rounding off. This is another important thing, at least for our integers and stuff. Again, we stick with the NCRT rules. The first thing, if your last digit, I'll show you with an example. So if the number is greater than 5, or you can say if the nth digit is greater than 5, then the n minus 1th digit increases by 1. Example. Let's say if you have 7.3647, something like this, and someone tells you round off this to 2 digits. Something like this. Now be careful here. When you round it off, 7.3674, you want to round off to 2 digits, right? So if you want to round off the 2 digits, then look at the third digit. Don't start from the tail. So you want to round off to 2 digits, so look at the third digit. What is the third digit here? 6, greater than 5. So this becomes 7.4. What about these two? We don't care. You can have, no matter how big tail you have, you start from that. For example, if someone says round off this to 3 digits, then we look at the fourth digit, so 7.3674. So we look at the fourth digit, which is again greater than 5. So I'll write this thing as 7.37. So we don't start from the tail. We don't start counting from 4. Okay, 4 is there, less than 5. So this will be 7, 7 greater than 1. This is it. You don't do that. That actually adds up the error. So even if there are 20 digits, if they ask you for the third digit, you start from the fourth. You don't care about the tail. If the nth digit is less than 5, then n minus 1th digit remains same. Again, something like this. So let's take a number. Let's take that number only, 7.3674. And let's say someone tells you to round off to 1 digit. So if you want to round off to 1 digit, you look at the second digit, 7.3674. Your second digit is 3, which is less than 5. So you do nothing. Answer is 7. Let's say if they say round off to 4 digits. 7.3674, then 4 digits, look at the fifth digit. That is this guy, 7.367. You do nothing. So greater than 5, less than 5, you're clear. Any doubts on this? Then the headache is, what if it is exactly 5? So NCRT has some weird rule, so we'll follow that. No idea why they made that weird rule, but if the digit is 5. And if n minus 1th digit is odd, then the n minus 1th digit increases by 1. I don't know why they allow odd numbers. If n minus 1th digit is even, then n minus 1th digit remains same. Let me take an example. Let's say we have 8.345 and we have 8.335. Now, if I round off this to 3 digits, look at this thing. So we want to round off here. This is 5. This number is even. So according to the rule, you do nothing. So this will be 8.34. This is 5 and this is odd. So according to the rule, you have to increase by 1. This becomes 8.34. This is the weird rule you have. They're in NCERT, so we'll stick to it. They do actually use this convention in other places also, but some people just say less than 5 is counted as, there's nothing called equal to 5. So they count anything less than equal to 5 as nothing will happen. Greater than 5, they will increase it by 1. But in NCERT, we have this one weird rule. So even and odd. Clear? Great. So let's see one example on this. So we have a number 6.7558. Round off this number to 5 digits, 4 digits, 3 digits, 2 digits, and 1 digit. So just get all of them. I should put some centimeter or something, but okay. Round off this to 1 digit. Yeah, let's get them both. Finish off. I'll give you a minute, then I'll show you the answers. You can verify. We should finish all this in the next class. Next class will start off with the loss of motion introduction also. Done. So you want to do 5 digits. So that is 8 there. So I will increase the number by 1. 6.7356. 4 digits. So I look at the 5th digit. So that is a 5. And the number before it is odd. I should increase this. So 6.736. For 3 digits, again, that number is 5. Again, it's a number is an odd, so 6.74. For 2 digits, that is 3, so 6.7. For 1 digit, that is 7, that is 7. Check. What about this guy? 43276, round off to 1 digit. How will you write this? It's not 4, huh? Number is 3, so you have to make it 4. So you will write this as 4 into 10 power 4. So Don't write 4. 43,000 doesn't become 4. 43,000 becomes 40,000. But you don't write 40,000, you write 4 into 10 power 4. It has one SF. Clear with this? All clear with the rounding of rules? So now you know what to do with the integers. So let's say you're solving a question and you get an answer in the integer 2 by 3 or something like that. So then you have to report up to 2 decimals in the answer. So you'll get 0.66666. So it is 6 greater than 1 to 0.67. You round off up to that last decimal. So in JEE Advanced, right, you have to report the answer up to 2 decimals. You will see the numericals there. So next. So how do you add this and subtract these measurements? Addition and subtraction. So while adding and subtracting, the measurement should have same number of decimals. Think about it. If you measure two things with two different instruments, your final answer can't be more accurate than the least accurate instrument. Meaning your final reading is as good as the instrument with the least accuracy. Adding and subtracting the measurements should have the final measurement. Same number of decimals. So because if you remember, I told you the decimals will tell you what kind of scale did you use. So same number of decimals as the measurement with least decimals. So example, let's say someone tells you 1.23 centimeter plus 3.145 centimeters. This thing has 2 decimals, that thing has 3 decimals. So first what you do, just add them up. 1.23, 3.145, 5, 7, 3, 4. Now, if you see, this thing has 2 decimals. Means you're accurate up to only 2 decimals. This is 3 decimals. So if you add an accurate and an inaccurate result, you'll become inaccurate. So we need to round off to 2 decimals. That means I need to look at this number here. That is 5. 7 is odd. So I will increase by 1. So the final answer is 4.38 centimeters. Clear how we report that? So rounding off, addition, you can see the rules will pile up on one on top of another. So suppose if I had to add 6,000 minus 23.7, both are centimeters. What do you think I should do? This thing has 0 decimals. Matlab, your final answer should not have any decimal points. So first subtract. First, you always have to do the normal thing and then 23.7. So this thing would be 5976.3. So you don't want any decimal. So this is 3 less than 5. So 5976. Clear with that? Easy stuff. So I'll give you a few additions, just finish it off. 7.34 centimeter plus. Luckily in the exam, right, these questions are actually easy to solve. They won't expect you to exactly add and do stuff, but they'll expect you to look at the number of decimals. So there'll be 4 options with different number of decimals. You just see which will have the decimals matching and you can mark the answer. 323 centimeter plus 0.41. Yeah, let's get the mole. So what is this? So just first add them up. 7.34, 2.2, that will be 9.54. But this thing has only one decimal, so that's your least one. So 4, so round it off. So this is 9.5 centimeter. That's what you'll report. You don't report 9.54 even though it is there. So this thing is 323 plus 0.41. So there are no decimals there. So this would be 323 only. So when you add them, you'll get 323.41. You can ignore that last 41. What about this guy? 45, 613, 4.1, 2.23. Calculate. $43.743. But this thing has only one decimal. So examiner, they're not expected to calculate. The options will be like this. 43, 43.7, 43.74, 43.743. So one decimal, so that is 4, so 43.7. Easy. So addition, subtraction, add them, subtract them, end में just see who has the least number of decimals. The final answer cannot be more accurate than that. So the logic is simple. The 4.1 meaning you used a scale that has only like what? 10, 10.1, 10.2 and so on. So this is the kind of scale you used. 2.23, you used a scale which is 2, 2.01, 2.02, 2.0, you know, to 2 decimals. The scale is really good. So you took a value which you measured very good and you took a value which is messed up. And if you add them, you'll get a value which is messed up. You can't become more accurate. It's like if you take 1 liter of milk and if you put 2 drops of poison, what is it? Is it milk or poison? It is still poison only. You can't dilute it. So you mess up that thing. So next thing, multiplication and division. So rules are different. You have to follow them. These kind of questions do come in mains, bits. They do ask a lot. Advanced, they will be as a part of a question. They'll give you some Wernicke calculus or something. They'll ask you to do some measurements and then you'll expect. So here, the result should have same SF, not the decimals, same significant figures as the measurement with the least SF. Example. Let's say we have 2.22 into 1.1. So that will be 2211. 2442, so 2.442. Now look at this thing. So this guy has 3 SF and this guy has 2 SF. So your final answer should also have 2 SF. Means I need to round it off here. So this is 4, which is less than 5. So the answer is 2.4, whatever is that unit. Let me take one more. If you have 442 centimeter by 2 centimeters, what about this thing? 221, but this thing has only one SF. This thing has 3 SF. So you're not supposed to write 221. You should have only one significant figure. So this is 2 into 10 square. But same thing, if you write it as 442 centimeter by 2.0 centimeter, now suddenly this thing will have 2 SF. So this will be written as 221, which is 2.2 into 10 square. If this is 442 by 2.00 centimeter, now you have 3 SF. So this is 2.21 into 10 square. You're getting how the answer is changing? It looks like you're dividing by 2 in all the cases. You're not. Clear with this? Same thing with the division also. When you divide, multiply, these are the rules. You have to have the same SF as the measurement with the least SF. Great. So let's do a few questions here. 3.2 centimeter into 1 centimeter. What is the final reading? Get the 6 questions. Let's see the first one. So 3.2 into 1 is 3.2 centimeters square. But this guy has only one significant figure. This thing has 2. I need to round it off. So that will be 3. 3.2 has 2 SF. So, and that 2 is less than 5. So if you round it off, it becomes 3. This guy is how much? 6, 6, 6, 6. 1, 2, 3, 0 centimeter square. But this thing has only one significant figure. Remember, 6,000 is not 4. Those zeros are useless. So we need to round off this 6 here, which is greater than 5. So this will become 7. And how many digits are there? 1, 2, 3, 4. Did I miss 1 0 extra? 7 into 10 power 6 or 7. I think it is 6. Check it out. So that thing has only one SF there. This one, 14.28 by 0.74, that looks, now again, be careful. This thing has 3 SF. your final answer should also have 3 SF. So even though it looks like 20, you should write it as 20.0. Because if you just write 20, this thing has only one SF. So how do you get three significant figures? 20.0. So 20 is not acceptable. What about this guy? 440 by 20. This is 22. But this thing has only one SF. So this is rounded off to 2 into 10 power 1. That's the difference. You should make sure like this thing is coming out to be like 20. You can't write 20 because you have 3 SF there. So 20.0. E is a good question. E came in the exam. Any doubts on ABCD, please ask. Try. E, give it a try. Okay, let's see. So the length of a cube is 8 centimeters. So the volume of a cube is L cube, which is L into L, which is 8 centimeter into 8 centimeter into 8 centimeter. This is 512 centimeter cube. But your measurement has only one significant figure. So this thing has to be rounded off to 5 into 10 square centimeter cube. The answer is 500. Play with this. So if you say, no, it should be 512, then you should have given, if length is 8.00 centimeter, yeah, then volume would be 512 centimeter cube. If your length was 8.0 centimeter, then your volume will be 5.1 into 10 square, means 510 basically. Clear with this? Simple one, but you can clearly see 512 when you'll put it. What about this guy? Root 6.5 minus 6.34. Try. I'll give you a minute for that. How will you do that? So when you do this thing would be root over 0.16. Right? 0.16 can be written as 16 by 100. So that will become 0.40. Now, if you look at here, this thing has only 2 SF. So even the square root thing will follow the division and multiplication thing. So this thing also has 2 SF. So 0.40 should be written as 0.4. You need two significant figures, isn't it? So 0.40, both are counted actually. That's how you write. This thing has 2 SF. So even your square root follows the same rule as multiplication and division. So in multiplication and division, we should have the same number of SF as the least. That way. Clear with this? Let's see one more. If you got this, I think then things are clear. Let's say length of a rectangle is 4.32 centimeters. Breadth of a rectangle is 2 centimeters. Find area. Find twice the length. What's the catch? Area is length into breadth. 4.32 into 2 centimeters. This would be 8.64 centimeters square. But this thing has only 1 SF. So we need to round it off. The answer would be 9 centimeters square. The second thing, you're asking twice the length, means you're asking 2 into L, which is 2 into 4.32. Be careful, this is a constant. That means this will have infinite SF. So it is exactly 2. There is no error there. This thing has 3 SF. So the least number of SF is 3. So therefore, this answer is 8.64 centimeter. Clear with the difference? They look deceptively the same. They're not. So this thing you would report as 9, this thing you report as 8.64. Even though it looks like you're multiplying with 2. Here you multiplied with a measurement, here you multiplied with a constant. Clear with this stuff? These are rules of significant figures. You do get questions on this, so you will understand this. When you look at the options and all, let's see. In physics, if they ask you length of a rectangle, breadth of a rectangle, and find area, that itself should give you some kind of a feeling like, what the hell? Who asks you area of a rectangle in 12th physics, isn't it? So then you should know, boss, this thing is related to SF. So that's the only way to figure it out, like find a volume, addition, subtractions. No one is going to ask you that in physics like a regular question. So don't get scared, like, if they ask you something like this in laws of motion or kinematics, it's okay. Even if you don't round off there, it works out. But some questions specifically, they will ask based on this. Okay, that's a bit about the next thing. We'll start off with errors after this. So take a break, come back by 9:40. We'll continue from here. So any doubt so far? Anything you're not clear? Please ask me. I'll send you a sheet on this thing so you can do it. It's like, yeah, you can finish off in an hour. Any doubts? Chalo, come back by 9:40 then.
Sir, what was the surface area of subparty?
वो भी है ना, भूल गया हमने. Surface area 6a square ना. 6 is a constant and this is a into a. How much is that? 8, 8, 48, 48, 6, 250, 238? No, 50, 300 to 88 centimeter square, but you have to do only one SF. So that will be 3 into 10 square. ठीक है?
Sir, that would be 384.
8, 8, 48, 6 ना?
Sir, 8864.
Ah, you're right. कितना आ रहा था?
Sir, 384.
then ठीक है, 400.
400, yes, sir.
You're right. Yeah, hands on everyone. Let's start off. Next time, errors. That's our main one. So what's an error? So it's the difference between the actual value and the measurement. Now there are two words, which we keep using. Sometimes we mix it up, but they have completely different meaning. Precision and accuracy. They're completely two different words. So precision is how close the measurements are. Meaning you can have wrong values, but all those wrong values are very close to each other. Others, do keep your cams on. Accuracy. How close the measurement is to the actual value. I'll show you what it means. But luckily for us, right, in NCERT level, precision is simply number of decimals and accuracy is simply how close you are. So that is what NCERT says, but the meaning is something else. Whenever you want to talk about precision, you can't talk about a single value. You need a bunch of values to check whether it is precise or not. But anyways, how close the measurement is to actual value. The best example, right? Let me put a picture. It's not here, I guess. Units and dimensions. I should have saved it somewhere. Why is this so slow, right? I think it's not here also. Shit. This is the last place it should be. Where did I keep this? Capacitor, basic math. Shit, errors is there. Need to have some really good questions, but unfortunately, we won't be able to do all of them now. We need other chapters to get over. Look at this. So let's say if you're shooting a target, right? Like I said, you're not doing it for a single thing, you're doing it for a bunch of things. So look at the first value here. You have shot it all over the place. So this is the central target, you're hitting everywhere. So this is a low accuracy, low precision. Look at the second one. You're hitting, everything is wrong, but all of them are pretty close. This is called high precision. So precision has nothing to do with whether you're right or wrong. all your measurements are coming as close as possible. Look at this thing. This is a high accuracy. All are pretty close to the center, but low precision. Again, it's comparative. This is high accuracy and high precision. I think the picture is explanatory, right? But how they frame questions is like this. Example, let's say the actual value is 4.423 centimeters. Let's say this is the actual value. So if you give me 2.413, this thing has the same number of decimals. So this is precise, which is actually a wrong definition, but this is what they actually use in CET bits and mains. They think precision meaning more decimals, but this is less accurate. So you have to stick with that because you can't talk about precision and all with a single value. You need a bunch of values to talk about precision. So since this is precise because you have same decimals, but more decimals, but less accurate. If you have something like 4.413, yeah, you're precise and accurate. Again, it is always relative to the previous guy. If you have something like 2.0, this is imprecise and less accurate and less precise. So in the exam, if they give you 4 values and ask you which is more precise, they're expecting more number of decimals. But the whole meaning of accuracy and this thing is something else. So if you have 4.4, this is less precise because your decimals are less, but it is accurate because you are getting the first 4 at least. So more accurate. Again, accurate, less accurate is all comparative. But anyway, that is the one thing. So just the words there, precision and accuracy. Next thing. Now, whenever you give a measurement, right, you are not supposed to give a measurement like if I ask you what is the length of a scale or something. If you say 10 centimeters, that is wrong. This you will understand tomorrow if you actually get into construction, right, and manufacturing. You will need to know. For example, look at this thing. If you bring a carpenter and tell him, right, I want a door. Okay, he will come to your house. He will look at the door ka frame and he will get that scale or whatever, he will measure it, right? And if you look at that thing, right, he generally uses that centimeter thing, which has millimeter divisions. So he measures the door ka width and he gets something like, 20 centimeters or something. So he will write 20, right? He'll manufacture thing. Now look at the problem with this. When you say 20, what is happening is there is always an error of plus or minus 1 centimeter. Right? Because you're simply saying 20 there. So that guy, when he manufactures, right? So that's a tolerance. 1 centimeter, he really doesn't care also. He will go and make a door of 20, 21 centimeters. Let's say if the door becomes big, what do you think he will do? He will get a machine. He will just shave off some of the wood here and then he'll try to fit it. If it was a little loose, what he will do? It says, okay, that's big deal. Meaning who will going to come in that small gap, isn't it? But what if you have to manufacture a door for a submarine? Will you still do the same thing? That's a problem. So tomorrow, right, if you're manufacturing, you will know this once you go to college, right? IIT, NIT, bits, whatever. And if you're doing in a lab and you're manufacturing something, let's say you're making the leg of a robot or something, and they'll ask you that what is the size of the screw or what is the size of that hole that you have to make. If you say the size of that diameter of the hole should be 2 centimeters, they'll kick you out. You have to be precise, 2 centimeter plus or minus 0.1 millimeter. Meaning you're telling them, boss, it has to be 2 centimeters and I do not want an error more than 1 millimeter, meaning it is supposed to be 0.01 centimeter, meaning 1.99 to 2.01 is an acceptable error. Anything out of this, you're gone. This is called precision engineering. This is the difference between, a company manufacturing bottles for Surfka bottle and a medical company manufacturing a bottle for medicines. Both are completely 2 different things, even though both are plastic bottles. The companies which supply bottles to medicines, right, they are more precise. They have to be more precise. Imagine you're putting eye drops and you press it and half the bottle falls in your eye. You don't want that, right? So whenever you press, there is a precision that certain amount has to come out. What if you're manufacturing a door for a spaceship or something? They have precision up to 10 power minus 5, Even air molecules cannot escape through that gap. You need a precision of that sort. So, and it becomes expensive. If you go and ask someone, right, give me a rod of 10 centimeters plus or minus 0.1, let's say copper rod, maybe it will cost you like 50 rupees. If you say, give me a rod 10 centimeter plus or minus 0.01 centimeter, this will cost you 300, 400 rupees. If you say, give me a rod 10 centimeter plus or minus 0.001 centimeter, this will cost you a lakh. Because you can't get this kind of a precision with your blade. Because your blade width will be more than this, you have to do laser cutting. So yeah, that's the thing about precision and stuff. So whenever you say about length, right, you should always report it as L plus or minus delta L. The delta L is your error, or sometimes also call it tolerance. Up to that error, I'm okay. Example, 10.0 centimeter plus or minus 0.1 centimeter. This is how they report the answer. Meaning the instrument you used has an error of 0.1 centimeter. So the other guy who's manufacturing according to you, he will keep this in mind when he's making whatever that you asked for. So it should be between 9.9 centimeter to 10.1 centimeter. That's the meaning of it. So if you have a quantity P plus or minus delta P, then we have few terms here. We call it fractional error, which is simply the error by the value. Percentage error, which is the fractional error delta P by P into 100. Example, if you have L is equal to 20.0 centimeter plus or minus 0.2 centimeter, then the percent error in L will be 0.2 by 20.0 into 100. That comes to around 1% error. So sometimes they'll report the answer like this, 20.0 centimeters plus or minus 1%. That's another way of representing an answer. Okay, how we report an answer? Now, how do you do a measurement actually? So if they give you a scale and if they give you a rod and ask you to measure it, you can't just measure it once and give. You must have gone to a lab anytime, you must have seen, right? You don't measure it once, you measure 10, 15 times. They ask you to take multiple readings, meaning I don't think you must have gone to a lab. If you go to a lab, you have to do it multiple times. So listen to this thing. So I'll show you one example and then we'll see some questions on it. So consider an experiment of measuring length. So you take a scale or some instrument and you take that rod and you measure. So the first reading L1, let's say you get 10.2 centimeters. Second time you measure again, you get 10.1 centimeter. It happens a lot. The same thing, you get different things. Let's say you get L3 17 centimeters. And let's say if you get L4 9.8 centimeters. We get L5 9.9 centimeters. You get L6 10.0 centimeters. You go with the 6 readings to the person. First thing when you look at this, definitely you're sleeping when you're taking this reading. Right? You're sleeping or you must have got distracted or something happened. A friend must have come and knocked you out. Because look at that, it looks so weird. Like everything is pretty close to 10 and that's the one big error there. So when you have something really odd one out, we ignore this. And that's the reason you should take a lot of readings. Imagine you take the first reading, you got 10.2, second reading is 17, and you stop the experiment here. Do you know what is the actual value? 10 or 17? You get in the problem there. But let's say I do one more experiment, I get 10.1. Now it looks like 17 might be wrong, right? But still, the probability, there could be a chance you messed up the 10 two times. The third reading says 9.9, fourth reading says 9.8. Now, can you see what happens? The probability that 17 is right and these are wrong is very small. So the more readings you take, the more sure you can be, boss, 17 is a nonsense answer. So that's the reason you should take multiple values. Even by chance you forgot and you included 17, if you take 100 readings, the error will take care of itself. So yeah, but if you're taking only 5 or 6, we are going to kick that 17 out from the reading. So remaining readings are close to 10. This is too far. Generally, they have never asked anything like this. So they'll generally give you like normally. But if at all they do, you can do this thing. So this in a lab, you're not supposed to take the 17. But let's say if you ignore this and you want to go ahead, then maybe you take 1,000 samples, then it would work out. That 17 really won't matter in the long run. Great, you got these readings. Now what you do, you measure the average value. This is how you actually measure the length of the rod, which is L1 plus L2. L3 we kicked out, so we won't measure it. L4, L5, L6 by 5. These are the only 5 readings we have. When you add them, I gave good numbers there. So that will all come out to be 10.0 centimeters. So we treat the average value as the actual value. So actual value, no one knows. We treat the average value as actual value. And then we report the error delta L is the average value, L average, minus the measurement. So now we are thinking that 10.0 is the actual one. Now we measure the errors. So the reading and the error. So L1, what was the reading? 10.2. What was the error? So delta L1 is the measurement, which is 10.0 minus 10.2, which is minus 0.2. So that is the error in the first reading. 10.1. Error in this is 10.0 minus 10.1 minus 0.1. L3 we are not counting. L4 9.8. Delta L4 will be plus 0.2. Delta L5 is plus 0.1. Delta L6 is 0.0. So these are all the errors we have in this. Then we take the absolute error. This is the process you have to follow. What is the absolute error? You basically take the magnitudes. Only the magnitudes, you don't take care about the sign. And we will see later on why. Because in physics, right, we always assume the worst case possible. But then we put a mod, so 0.2 plus 0.1 plus 0.2 plus 0.1, and the last one is 0 by 5. We take the average of all these errors. I know it's a big process, but this is what you do. And then you add all this, you end up with a 0.6 by 5. The 0.6 by 5 is 0.12. Now again, remember, this 5 is a number. It has infinite SF. At this 0.6 has only one SF. So we need to round it off. So this thing has two SF. So this will become 0.1 centimeter. So therefore, your final answer is this is how we report it. So length will be your L average, which is 10.0 centimeter. The error ka average absolute error is 0.1 centimeter. The percent error in L is 1%. Clear how we went long. So, but this is the process to get the length. Got the idea? I'll give you one like this. Now you guys try. Any doubts on what we did? Again, listen what we did. They gave you readings. They will give you this and they'll ask you find the reading or the measure the length. You get the average value, right? You take the average value as the actual value. Then you subtract the average value from the initial values, and then you take the absolute error and you're done. So let's do one question like this. That's the best way to learn. Consider an experiment of a simple pendulum. The So you brought a clock and you're measuring the time in a simple pendulum experiment. And these are the readings. T1 is 5.10 second. T2 is 5.05 seconds. 4.95 seconds. 4.80 seconds. 5.20 seconds. 4.90 seconds. Yeah, fine time, meaning we're expecting the error also. Percent error in time. Yeah, get it. It's just all calculations brute force. There's really not much to think. Any answers? You can give me the percentage error that should take care. Okay, let's see. What happened? Why did no one get it? Was it too tough? Something did I give wrong? Okay, so first thing, let's add them up. So just get the average. I gave good numbers, so you should get 5.00 seconds. Then we find the error. Just t average minus t, which is minus 0.10 minus 0.05 plus 0.5 plus 0.20 minus 0.20 plus 0.10. Perfect. Then we take the absolute error. Someone did get it. Shrikant 2.3. Let's see. Then we take the absolute error. That would be minus 0.10. By 6. So how much is this? 35.7. 0.70 by 6. This thing comes out to be 0.101340, close to 6. 36. Again, 4066. It's repeating there. So that we can. This thing has how many SF? This thing has 2 SF. This thing has infinite SF. Remember that 6 is a number. So we need to round it off to here. So this becomes 0.12 seconds. So the time is given by 5.00 plus or minus 0.12 seconds. The percent error in time will be 0.12 by 5.00 into 100. That 100 is a number anyway. How much is this? 2.4%. Clear with this? Check it out. I hope I didn't goof up any calculations, but yeah, that's how you do it. If you had actually only 5.1, 5.0 thing, then this would be only 0.1 again, because there are 2 decimals that 0.12 will become. This is what would happen with that rounding off, and all those formulas will come like this. Clear with this? This is one type of problems you'll get in errors. They'll give you a bunch of readings and they'll expect you to get an error from there. Any doubts on the process? Great. Have fun while this chapter is going on. After once NLM starts, things will be again different, like we had in kinematics. And that actually will be more fun. But in physics, right, you have few chapters like this. I call them inorganic physics. You have to remember a lot. Next thing, errors are of 2 types. Random errors. So this random errors, right? This happen due to external conditions. So basically, you really don't have a control over this. If you ever been to a lab, right, they have ACs in the lab normally, and they maintain the temperature 24. Those air conditioning is not for you. It's not for you to sit comfortably and do the experiment. It is for the equipment, because these equipment are designed to work at a certain temperature. Let's say you bring an equipment from Europe, there where the temperatures are like 18, 20, they normally design it to work at 24 degrees. They bring it to India, and during summer temperature goes to 45. Machine will start giving you all weird values there. Maybe the operator is different. You do the experiment today, and tomorrow you yourself will get different readings. Variability, of measuring devices. So yeah, just happens. There was a thing like this in software, right? Computers, right? They use the supercomputers to predict weather patterns. And what these people noticed, right? Every time they put a value there, the whole, even if you get the exact same values, that whole program gives you some other thing. That is because the error happened somewhere on, third or fourth decimal you can't see, and that small decimal propagates over a span of months, and the whole reading of the weather pattern changes. So there are certain things really you can't control. The only way you can decrease this, you take a lot of readings. So random errors can be decreased by taking a lot of readings and assuming they'll balance out. By taking a lot of measurements. The second thing is systematic errors. This happens maybe due to the procedure only. Your process itself is wrong. Or maybe the instrument is wrong. If you ever heard this term called parallax error. So when you're looking at a scale, right, you look it from the front. If you start looking from the side, it starts looking like you see a different value there. Maybe the way you're supposed to see itself is wrong. Maybe sometimes the instruments are bad. Happens a lot. I still remember in my first year of IIT, right, you have a physics lab. In first year, you have all labs. You have physics lab, chemistry lab. So we had an experiment on some prism. So I and my friend as a group, so we are doing the experiment. We spent almost 2.5 hours, I guess. After doing all that, we are not getting any reading there, and it was a mess. And then the instructor comes and says, "Oh, this table, the equipments don't work." After 2.5 hours, and we are like, "What the hell are you doing for 2.5 hours? You're roaming around. You couldn't tell us that even once that this table doesn't work." And then we had to take some other thing and we had to get it done. But happens a lot. Anyway, that's a bit about the errors there. Next thing. So how do you add errors? Addition and subtraction of errors. Imagine you have two scales. The first thing, the errors always add up. Because like I said, in physics, we always take the worst possible scenario. Let me just take the attendance. These people being, who is this? So let's say we have a length 10 centimeter plus or minus 0.1 centimeter. Understand the meaning of this. The length here can be between 10.1 to 9.9. That's the meaning of it. Let's say the breadth is 5.0 plus or minus 0.1 centimeter. So the value can lie between 4.9 and 5.1. Now ask yourself, if I take these two rods and if I combine them, what are the cases with the maximum possible error? What is the worst thing that can happen? You should always be ready for the worst possibility. So the worst thing that can happen, both the rods have positive error. So someone made a scale with L plus B where it is 10.1 and 5.1. This would give you 15 plus 0.2. The other worst possibility, you took both the scales short of 0.1, 9.9 and 4.9. This will be 15 minus 0.2. That means we can be sure when you add these two rods, the length will be 15 plus or minus 2 centimeters. Making sense why we add the errors? Because you're taking the worst case possibility. Similarly, when you subtract L minus B, again look at the problem. What is the worst thing that can happen here? You take L to be maximum. So the worst will happen when B is minimum. So that would be 5 plus 0.2. What is the another possibility? 10 minus 0.1. You take L is minimum and you take 5 is maximum. So this is the catch there. So whether you add or subtract, error always adds up. Clear with this? Because that's the worst thing that could happen. So errors are always additive. You add or subtract. Clear with this stuff. So yeah, that's the straightforward thing there. What happened here? Great. Let's see one equation of this. Let's say we have two resistors, R1, R2. When you combine them, you will get an R equivalent. Find R equivalent. Addition and subtraction are actually straightforward questions. We have a rectangle length L and breadth B. Find error in perimeter. Yeah, get them. Okay, let's see. So what is R equivalent? R equivalent is R1 plus R2. So you have to add both these measurements. How do you add them? Just directly add them. 30.0 plus or minus 0.4. बस हो गया एक ही step था. I didn't ask you for error, but 0.4 by 30 into 100. How much is that? 0, that's 10, 4 by 3, 1.33%. But this thing has like what? 0.4 has only one SF. So we need to round it off. That will be like 1%. I should have given 0.40 something, like then it would have been 1.3%. Okay. What about this thing? Perimeter is 2 into L plus B. So this is 2 into L plus B is 15 plus or minus 0.2. So the 2 gets multiplied to that also. This will become 30 plus or minus 0.4. Then, yeah, percentage error in B is 0.4 by 30. 15.0. Yeah, I think we got the same answer there. So clear with this? That's how you do for addition and subtraction, is the straightforward one. Next thing, we'll just do one more, then we'll continue in the next class. Power rule. Every time it won't be so easy to add and subtract. Sometimes the functions will be weird. Let's say if I have a function like a is equal to p power x, q power y, and r power z. Yeah, multiple things. Then how do you get an error for this? We actually do a little differentiation, put ln on both sides. This would be ln a. This would be ln p power x, ln q power y, minus ln r power minus z. Differentiate on both sides. This will be a very important technique. Meaning, for example, tomorrow they'll ask you like this. The range of a particle is given by u square sine 2 theta by g. And they'll say there is an error in speed of, let's say, 0.1%. There is an error in angle. There is an error in gravity. And they'll ask you find the error in range. So this thing, look at, say, u square is looking like p power x. Sine 2 theta is itself something else. G is something else. So they can play around like this. You will see a lot of questions like this. One of the reasons why I wanted to teach is because of this. Whenever the changes are very small, a simple question like this, a particle is projected vertically with speed u, right? And they would say if the speed is increased by 1%, what happens to the height? So they'll not say error. The words will be different. They'll say the speed increased by 1%. Then what you will do normally, 1.01 u square by 2g, this becomes really long. But if I use this logic, h max is u square by 2g. So I can treat this like an error and solve the problems. So we will see in the next class. So it's pretty useful that way when changes are small. Differentiate. So ln ka differential will be dA by A, chain rule. This will be x into dP by P, y into dQ by Q. That would be minus Z into dR by R. But when we take errors, we always take the additive. There is an exception though. We'll talk about that also later on. So dA by A is x mod dP by P, y dQ by Q, Z dR by R. This is valid. P, Q, R are independent of each other. That's one important statement. They never asked questions on that so far, but we'll talk about that in later on. So that's a pretty good formula. This is called power rule. So remember it that way. Example. Let's say A is equal to P cube, Q square by R power 4. Percent error in P. This is a straightforward CET level question. Bits also. Percent error in P, Q, R is 1%, 0.5%, and 0.1%. They'll ask you find error in A. So percent error in A, so you can directly put x is 3. into percent error in P plus 2 times percent error in Q, 4 times percent error in R. That would be 3% plus 1%, 0.4%, 4.4%. The questions would be of that sort. So addition of errors, subtraction of errors, and power rule. So more about this we'll talk in the next class. I can see most of you are exhausted. If you got over, chapter is lengthy and a lot more theory. But make sure to go through this whole thing. It's not a tough one. I think next class we'll finish off in the first half of the class. And then we'll start with NLM. Mostly NLM will start with the constraint equations. We'll start with constraints first. Okay, but in this, there is also something called Wernier calipers and screw gauge. That we are not going to do now. We'll do it later on when the portion gets over. There are other few things also, but that is useful when the portion gets over because you get a lot of questions from different chapters. But this much idea you should have. Okay, with that, we'll wrap up for the day. So we'll catch up again on Wednesday. We'll continue from here, but just make sure to just go through the notes once. And I hope last Friday ka paper, everyone solved it. The paper was good. If you have seen it, the questions were a little different. So just to resolve that, it's a good paper to learn from. Yeah, and okay, we'll catch up on Wednesday, same time. So any doubts, anything else, please stay back and ask, or else you're free to leave. And